All right, guys, so let's get started. So today we're going to look at the different heat transfer modes. So I'm going to call this section heat transfer modes. And this is actually quite important, guys, if your major is aerospace, because you don't have a class in your curriculum called heat transfer. So this is the only time you're going to see these heat transfer modes, okay? Unless you go to grad school over here. My recommendation would be like you have 2 tech electives. I think this is one class missing in your curriculum, okay? But let's see. What is a heat transfer mode? So basically in thermodynamics, the only thing we care is about when a substance goes from one state to another. So let's say you have water going from liquid state to gas state. In order for that to happen, what you need to do, you need to apply heat, okay? But the way you apply the heat is never of concern. We don't care, okay? So the heat transfer modes actually is what tells you how you apply the heat to a system. So there is majorly 3 different transfer modes. The most common and most widely studied, because it's the easiest one, is what is called conduction. The second one is convection. And the third one is radiation. Okay? So really these are fancy, well, not fancy, but these are the words used to define the different heat transfer modes. But basically what I like to say, which I think is more accurate, or at least makes more sense, is that conduction basically is the heat transfer mode that defines when heat goes within a solid medium. Okay, so for example, if you have a block of steel and you heat it, the heat is going to go through it, or it's going to flow through it through conduction. All right. Now, another one, which is convection, that one is more related to what? Convection is more related to fluids. Okay. So let's say convection. What is a convection oven? It's basically a normal oven, but what do they add to it? Just a fan, no? So that the air can move the heat around the oven. So it's more related to a fluid medium. Okay, or can be water, all right? And now the last one, radiation. What should be an example of radiation? The heat from the sun comes to the earth through space. And the heat transfer mode is radiation. But in space, there is no medium, no? So if you want, in order to have radiation, really, you can have vacuum medium. So obviously, every single case that happens in real life is not only one of these 3, it's a combination of the 3, but in most cases, 1 or 2 will be more dominant than the other one, okay? Okay, and so that's the way to study this type of heat transfer modes. So let's start by the first one, conduction, which is the most widely studied and also the easiest one. Conduction. Okay, so conduction, we say, is for solid mediums. Okay, so the typical figure, let's say you have here a brick. Okay, so let's say this is a brick. All right. So in that brick, let's say this is the outside. We are in Florida, so let's say it's hot. Okay, so I'm going to make here on this line here, I'm going to do a little sketch. It's going to be easier to understand. Okay, so let's say this is the outside. So let's say you are in Florida. So in Florida, what's going to happen? The inside, let's say, will be at a hot temperature. And let's say the heat is coming this way. Okay, so Q dot here, I will tell you what that is, but Q dot is the heat transfer mode. So there's heat coming that way. And let's say, obviously, inside, let's say it's cooler because whatever, there's no sun or you have the AC on. So let's say this will be T cold. All right? So between those 2 points here, you could relate this change in temperature by a straight line, which is called the temperature gradient. All right? So let's say this is your wall over here, brick wall. And let's say the thickness of that wall is L. Okay? And now, this sun over here, the sunlight that is coming, will be hitting which face? It will be hitting this face of the wall, no? All right, so this will be here the A, which is the, I will define that later, which is the surface where you have the heat being concentrated. Okay, and obviously the conduction also need to be able to relate of what material the wall is made of. So for example, you agree that the heat transfer is not going to be transferred the same way the wall is made out of brick, wood, steel, or any other solid material, no? So let's say there's a constant here called K, which defines the properties of the wall. And I will define now every one of these variables. Okay, so Q dot here basically means what? dq dt. All right, so the conduction is defined by what? So this Q is defined as Q dot equal, if you want, dq dt. I'm going to redefine that stuff. So now the heat conduction needs to be related to the material, which will be K. Also, what's going to affect is to know how much surface is being exposed to the heat transfer, A. And now we need to take into consideration what is the change of the heat over here throughout the thickness of the wall, okay? And that will be, so let's say dt. This is really L. So let's call this one here dx. Maybe this will be easier. It will be easier to understand. Okay, and now there's something that is not confusing, but if you look at the slope of this line, if we define heat transfer as positive as going from hot to cold, okay, this equation will give you what? K is a constant, so it has no sign, so it's positive. A can only be positive, but dt dx will be the sign of this. What is the slope of this line? It's negative, no? All right, so really if you do this calculation, this will give you a negative value, but since we define heat transfer as being positive when it goes from hot to cold, we need to add here a minus sign. Okay, so over here, if you want K is the conduction coefficient. A will be the exposed area. And dTdx is what is known as the temperature gradient. Okay. All right, so just here to, as an example, let's just look at some of the K heat conduction coefficient. All right. And I don't have the book with me, but that's not important. So let's just see what would be different values for this K. So let me go online. Let's see conduction coefficients. No, conduction coefficients. Okay. So hopefully it will be a list. Okay, I guess the same one. Okay, so basically, this is too technical. Just want to list. There we go, material and gases. So basically, I want to really look at just some materials. So let's say we look at the K, the thermal conductivity, okay? Well, the units will be watts divided per meter Kelvin. All right, so we're gonna put this stuff now. But let's say, obviously, if the material can transfer a lot of heat, the K should be high. If it's an insulation material, the K should be low. So for example, let's just look at solids, okay? I don't want to interested at, so balsa wood. What do you think balsa is a good conductor? Obviously not, okay? It doesn't stop, but it slows down the heat transfer to the material by 0.028, okay? Now let's look at a metal, brick, the one we're doing here, brick block. The brick dense about 1.31, brick fire 0.47, okay? The building brick is between 0.6 and 1. Now let's see, concrete, 0.4, 0.7. So all these ones are pretty good at slowing down the heat, no? They are small value. Let's try to find a metal. I'm just looking at the values. So which one is very high? Magnesium, so that starts being metals. They don't have aluminum. Okay, let's see, they have steel over here. Silver, they don't have it. I don't know why. Sand, they have steel. Yeah. They don't want to put the metals. All right, let's see if they have here steel, carbon, steel, stainless, see if they have the value. Thermal conductivity, this time we see aluminum is about 237, so these values are much, much, much higher, no? Okay, so that's the important part over here. Just remember that the units would be watts per meter Kelvin. So maybe let me add that to the notes. All right, so let's look at the units. So the units for K, watt per meter Kelvin, but all that makes sense because when you have Q equal to minus Ka dt dx, all right, what should be the units here of Q? Well, units of Q. So units, Q dot should be in watts for W. K, we already put it there. The units for area we use metric will be meter square, and dTdx should be what? Should be Kelvin per meter, no? Okay, so if you want, let's double check. So if we know these units, what should be the units of K? K is equal to Q, okay, just for the units, divided by A dTdx. So if you look at this, it should be equal to what? Watt divided by meter square times Kelvin meter, no? So you see right away that what you get over here, you will get what we had on top. Watt divided by meter Kelvin. Okay? All right. So let us do an example right away. And let me try to find that example from the textbook. All right, so we're gonna do problem 248. We do 247, but I think 248 looks better. So as shown in figure 248, an oven wall consists of a 0.635 centimeter thick layer of steel with Ks equal 15.1 and a layer of brick K equal to 0.072. At steady state, a temperature decrease of 0.7 occurs over the steel layer. The inner temperature of the steel layer is 300 degrees Celsius. If the temperature of the outer surface of the brick must be no greater than 40, determine the thickness of the brick wall, so LB, I'm guessing, in centimeters that ensure this limit is met. What is the rate of conduction in kilowatts per meter square of the wall surface? So let's do this figure, okay? Do on the page this figure, so it's from 248. And just do that figure over there. So still. B L B. Okay, so they tell you that the outside here, T sub I is 300 degrees Celsius. The T outside here needs to be lower or equal to 40 degrees Celsius. And the loss in here, the delta T here is negative 0.7 degrees Celsius. Okay, so that's the figure that I did over here. And basically they ask you to find LB and Q dot per meter square in kilowatt, sorry, so this is Q per unit area, A, which will be kilowatts per meter square. Okay, so in this problem, the important part is this one. This is the whole understanding of this problem, is that the heat here, heat transfer mode, is Q dot. Okay, so the steel and the brick cannot stop the heat going through, but they can slow it down. Okay, but you cannot stop it. If you give it enough time, all this heat is going to go through. All right? So what does that mean? Is that the heat here is always going to be the same, no? To the steel, to the brick, the amount of heat going at the end of the day is going to be the same. All right. So here we know that the main heat conduction mode will be conduction. All right? So what can we write? We can say, let's say, Q dot going through the steel will be equal to what? Minus K of the steel times A, which is the exposed surface area, that in this case is the same for the steel and the brick. Imagine here there is like this will be the exposed area will be like all this, no? All right, we do it in 3D. So it will be the same for the steel or the brick. And now here, for this one should be, the general definition is dt dx. Okay? So in this case, since we don't know the area, and actually ask us to find this in function of the area, we can say that this would be equal to what? Q of the steel per unit area would be equal to minus Ks dt dx. Okay, I'm going to try to do everything symbolic in the end. So Q sub S over A should be equal to what? I'm going to put here K sub S. I'll give it positive now. What should be dt dx? Dt dx, the amount of heat going through the steel, no? Yeah? So remember, we need to look at what is the temperature gradient per unit thickness going through this. So we know it's negative, so what is this value? Should be the change in temperature throughout the steel, they give it to us to be equal to negative 0.7. So a negative would become positive, so I can just take 0.7. And now what will be the thickness of that wall will be L sub S. Okay, so put here L sub S. And let's say this will be our equation A. Am I recording here? No. I'm recording, no? Okay, okay, good. All right. So this is the amount of heat going through the steel. Now, let's do exactly the same thing to know what is the amount of heat going through the brick. Okay? So we do the same thing. Q going to the brick. This time should be equal to what? Minus K of the brick, A, dt dx. Okay, so this one's going to be, let me do a figure, might help a little bit. All right, so this will mean over here that Q of brick per unit area will be equal to K of the brick minus KB of the brick dt dx. Okay? So over here, we know the outside from this figure over here needs to be, let's say, lower than 40 degrees Celsius. Now here, the inside this problem is not well spelled, but they say, okay, if this is 300 on the outside, and we know that the heat is going to decrease 0.7 degrees on this one, what should be the temperature right at this edge over here between the steel and the brick? It should be 299.3, no? Okay, so it's over here. We'll have the temperature. So let me call this one T contact 299.3. All right. And here we'll have now the line again. This will be delta T, the new delta T. And this is the LB that we need to find. All right. Okay, so we could say that this would be equal to what? Q d sub A will be equal to K sub B. Really, if you want to do the slope, what should you do? You should do like 440 minus 293 will be negative, no? But if you go from right to left, actually you don't need to worry about the negative value. So remember, this is the same Q as before. So over here, let's say we have T contact. So let's say this will be, I mean, let me put the minus, doesn't matter. I put the minus. And then we need to do what? The change of the slope will be what? T outside minus T contact, which is a 299.3. What is the thickness? L of the brick. Or this would just be equal to the and this would be equation B. Okay, so here what is important to realize, because this is generally a mistake that people do, is that they say that the total amount of heat going through this wall, composite wall made out of steel and composite, is equal to Q of the steel plus the Q of the brick. But that is not correct, because what did we just say? We just said that the amount of heat is the same, no? Okay, if this is, imagine heat transfer is very similar to electrical engineering in electricity. It's like if you have a current going through this resistance, that will be steel, and then you have another resistance in series called brake, the amount of electricity going through each one of the resistance will be the same, no? This is exactly the same thing. Think about Q being the current and steel and brick being these two different resistances, okay? So in that case, what do you know? You know that Q, this is the important equation, Q equal Q of the steel equal Q of the brick. Okay, so this is the equation I want to see in an exam. If I don't see this one, you are not showing me that you understand the material. Or since all three are subjected to the same area, I could just say Q dot of A equal to Q transfer going to the steel for A, Q dot of the brick A. Okay, so obviously using this, what I can rewrite what? K steel delta T over L steel, which is equation A. I just rewrote this equation. Equation A will be equal to equation B, which is KB over LB Tc minus T naught. Okay? And over here, let's not forget, Ks is given to us. This delta T over here is given to us. L sub S is given to us. I did not write it down, but it's given to us. All these temperatures are known. So the only unknown over here is LB. So we can go and solve for LB. Okay, so this will give us what? I mean, we could solve right away. LB will be equal to what? K brick over K steel then we'll have here can put it at the end. Okay, so I move that one. Okay, then we have Tc minus T outside divided by delta T. And all this needs to be multiplied by L sub S. So basically, you see what happened is that this will cancel the units of the K. This will be unitless as well, so you end up just with the units of the length of the steel, okay? So this is the answer. So if in an exam, you give me this, you probably get 9 or 8 points out of 10 because you're showing me that you understand the material, okay? Now, let us do the numerical application. So L sub B should be equal to what? So let's see. Let's look at the values that we had on the problem. So K sub B, that was on the other page. K sub B is equal to 0.72. It will be 0.72 divided by K steel, which is 15.1. Okay, now T contact was which one? Was the temperature of the contact where the steel and the brick are in contact. So we said that was 299.3 minus the minimum temperature on the outside is 40. Be careful here because I'm doing something which is correct, but we need to talk about it in a second. And the delta T, this delta T represents the change in temperature that was going through the steel, no? Okay? We know that one is equal to 0.7. And that the initial length L sub S of the steel is 0.635. So we need to be careful here. That's 0.635. If we keep 0.635, that will give us the answer in centimeters. Do we need to give the answer in something special? So, okay, we give the answer in centimeters. So 0.635, but this is in centimeters. So we should get the answer in centimeters. So be careful here. All right, so one thing over here, because it's gonna work because in this case, but what should be the units for temperature? The units for temperature should be Kelvin, no? So you want to be 100% accurate, you should move all these temperatures to Kelvin. But what happens if you do the difference between two temperatures in Kelvin? It's going to be the same as if you do the difference in the temperature in Celsius, no? Okay? So the same thing over here. This is the difference of the temperature between the outside and the T contact where the steel is, no? But if you really want it to be accurate, you need to use this as the to use these temperatures in Kelvin. So if you do this calculation, okay, so if you do the calculation, this will give you 11.22 centimeters. So basically, what this means is that the minimum thickness of the brick wall, in order to have a temperature, 40 degrees Celsius or lower, must be 11.22 centimeters. Okay? So now the second part of the question actually is very simple. They ask us to find what? To find what is Q over A. But what did we say? What is the important equation here is that we said that the Q over A is the same everywhere. So that means that now we should be able to find Q by either looking at the Q going through the steel or at the Q going through the brick. Okay? So we should be able to use either one of the equations. So let's do that. And if you want, you can check. So okay, so Q over here, Q over A can either be equal to Q brick over A or Q steel over A. So let's say we use whatever, Q brick. And let's do it both ways and see what we get, okay? So this should be equal to what? Minus KB dt dx, but we know this is equal to KB is equal to 0.72. dt, we know that one on the brick was equal to the one we had before. So which is this one here, which is the 299.3 minus 40. Okay, and this is divided, we calculated the LB. So be careful here because we have to change the units. This is going to be, we need to move the 11.22 centimeters 2 meters. So that will be 0.1122 meters, no? Okay? So we're going to do the calculation in a minute, and they want to have the results in kilowatts meter square. But again, you could also do what? This should be very close to Q steel over A, which is equal to minus Ks dt dx of the steel, which is equal to what? 15.1. Then we have the delta T over here, which is 0.7 divided by the, again, 0.635, was that centimeters or meters? So we need to move that in meters, it would be 0.00635. Okay, and by doing it both ways, we should get the same result. So for the steel, you get 1.665, and for this one, you get 1.664. But basically, they are equal, okay? Just a matter of decimals. Okay? All right, so remember the trick or everything you need to understand over here for conduction is that if you have heat going through a wall, the Q is the same at every vertical cut that you're going to do. All right? So let's say you have steel, brick, aluminum, copper, and so on. You can have different layers, no? The Q is still going to be the same, no? Yeah? Okay? That's what you need to understand over here. That's all you need to understand. Okay, so this will be the end for conduction. Now, second one is the most difficult one. But we don't do difficult in this class, okay? Is convection. So remember, convection, conduction was for solid mediums, and convection was for liquid mediums. Okay? All right. So let me give you the equation right away for convection. It's Q dot, which is dQ dt. So it's heat per unit time. That's why it's called heat transfer per unit time. Will be equal to H, which is the convection coefficient, times the area, same as before. And now let's say this will be temperature change. Let's say T hot minus T cold. Okay? So remember, I did not write it down, and maybe I'm going to repeat it. We assume the heat to be positive when you go from hot to cold. Okay? If you think about it, in what direction is the air flowing? Does it go from high pressure to low pressure, or from low pressure to high pressure? It goes from high pressure to low pressure, no? In the high pressure, the temperature is higher than in the lower pressure, okay? So that's the general movement of the motion of the fluid. So that's why we say that heat transfer will be positive from hot to cold, okay? So this is really the equation. Where A, again, would be the exposed area, and H is the convection coefficient. Okay, so over here, what would be the units of H? If you look at it, would be what? Units of Q are what? What? A would be meter square, and the temperature will be Kelvin, no? So the units of H should be watts, meter squared Kelvin. So over here, if I go and try to Google convection coefficients, do you think you're going to get something? So the answer should be no. I mean, you might get stuff, but for convection, they give you a rate of values, but they don't give you specific values for each one of the fluids, okay? And the reason being is, I mean, once I tell you, it's logical, but since it's a fluid, when you turn your fan in your room or in a room, is the heat convection, so the way the air will remove heat from your body, is it going to depend on the speed of the fan? Yes, okay? So let's say you go to the beach, you are hot, and you have air flowing on the beach. The way of the rate at which the heat will come out of your body will depend on the velocity of the flow, no? Of the wind, okay? Then, will also depend if you have, I don't know, if you are wet or not wet, if you have cream on your body or you don't have cream, solar cream, okay? Or any type, or anything. So it's not only on the properties of the fluid, but it's going to depend on the properties or the texture of the surface at which the air will be making contact with your body. Okay? Because what happens if you have a very smooth skin, the air might just come and slide on it. If you have a rough skin, it might go there and create some turbulence, no? So the convection coefficient is affected by a lot of factors. So basically, you cannot go and find an H value somewhere. So you need to calculate it for your specific case. And that is something that you will do maybe in a more advanced class called computational fluid dynamics. Sometimes you need to find what is the exact value for H, okay? Otherwise, there is some empirical formulas in order to find it in some simple cases. But what makes very difficult convection is that you don't know the value of H, because it's not that this equation is complicated. Okay, it's HA times difference in temperature. Okay, but to find H is very difficult. All right, so that's the only thing I'm going to write down. So H over here, very difficult. To determine because it depends on flow velocity and let me put it here, and shear with surface. So basically shear means the interaction with the surface, okay? So generally an H value will be given to you. All right, so let's go find a problem for this convection. Probably we're not gonna find one only for convection. Let's do radiation, and then we can go find a problem. That I think is gonna combine the 2 or 3 of them. So page 6. Okay, so radiation, the equation is Q dot equal dQ dt equal to sigma epsilon A T hot to the 4th minus T cold to the 4th. Where A, again, will be the exposed surface. Okay, here imagine you have a surface. You have the sun. It's going to expose some heat, okay? Let's say this is at temperature Tc, and the air is at temperature Th, okay? All right. And the surface here, we have an epsilon value, which is called the emissivity. And the emissivity is always between 0 and 1. So basically what it means, the emissivity is how much, or you could call it really the absorptivity, but in books they call it the emissivity, is how much heat, or how much of the sunlight, if you want, of the heat is going to absorb or reflect, okay? That's what emissivity means. So you all know that if you have a black car under the sun, it's going to be a lot hotter than if you have a white car. What is the reason? It's because the black car has one value close to 1, meaning that it's not going to reflect much of the light, but a white car will have a smaller value of emissivity. Okay? All right? And sigma here is called the Stephen Boltzmann constant. I'm not sure about the spelling, but we can check it now. And this value is equal to, so Stefan Boltzmann law, oh, I spelled it good, that's one constant. So there you go, you can write it down, is 5.670, no, but this one 5.670 for 10 to the minus 8 watt meter square Kelvin to the fourth. So let's say, let me write it down. So will be equal to 5.6704 10 to the negative 8 watts meter square Kelvin to the fourth. Okay, or if you want, in US units is 1.714 10 to the minus 9 BTUs per hour foot square Rankine to the fourth. All right. But again, that's not important. You should have all these values on your page with the different units. So this is what we have. Again, I'm not going to give you too much detail, but really, this equation is correct for the applications you do, but if you go into more detail, because do you think the absorptivity needs to be equal to the emissivity? So for example, how a body absorbs the heat needs to be equal to how the body gives the heat back to the medium? Is what happened in most of the material, but it's not what happened all the time, no? So really, if you think about it, this value here should be value for each one of these temperatures might be a different value, which changes slightly the equation. But for this class, this is good enough. So let's go back here to the book. And I know there is a problem. I think it's about a barbecue that considers all these ones. So let's do 255. Okay. So basically, just do the figure of the barbecue as I read the problem statement. So the outer surface of the grill hood, I'll put here example. Okay, so just do the figure. The outer surface of the grill hood shown in figure 255 is 47 degrees Celsius, okay? And the emissivity is 0.93, which is on the figure. The heat transfer coefficient for convection between the hood and the surrounding at 27 degrees Celsius is 10 watts meter square Kelvin, okay? Determine the net rate of heat transfer between the grill and the hood and the surrounding by convection and radiation in kilowatt per meter square of the surface. So basically just do the figure. This problem is pretty simple. Let's say this is a barbecue. We know that T0 is 27 degrees Celsius. So now here, be careful. So that would be how many Kelvin? What do you need to do? You need to add 273, no? So this will be about 300 Kelvin, no? Okay, 300 Kelvin. And the H value will be 10 watts meter square Kelvin. And now this is, if we look at the surface, T surface is equal to 47 degrees Celsius, which will be about 320 Kelvin, and they give you that the emissivity is 0.93. All right, you need to find the Q dot over A total per unit area. Okay, so that's my figure over here. Okay, so this problem is very simple. The total heat transfer, so the total amount of heat this is losing to the surrounding will be equal to what? You will have a Q that will be leaving by radiation, no? And then you'll have another Q, which is due to the air flowing around the barbecue that will be coming out due to convection, okay? So the total Q total, this time will be equal to the Q radiation plus the Q convection, okay? Since both are exposed to the same area, I could just rewrite this equation as what? Q total per unit area would be equal to Q radiation per unit area plus Q convection per unit area. Okay, so where, this is just a direct application, where we know that the Q radiation, what was the expression for Q radiation? Was sigma epsilon A T hot to the fourth minus T cold to the fourth. This is the general equations. So this means that Q radiation per unit area would be equal to what? Sigma epsilon Okay, let me see if we forgot something from the problem statement, the temperature. I don't think so, but let's check. Because that's not very hot. That's what I'm saying. 47 degrees Celsius is not that hot. Okay, that's fine. Okay, so over here, you'll be losing heat between what and what? You are losing heat between the hot surface, which is 47, no? So it will be TS to the fourth, and you are losing heat towards which medium? The air, which is at 27 degrees Celsius, no? Which is T sub naught minus T sub naught. Okay, Latin 1 or Roman 1. All right, and the other equation we need to know is that Q convection is equal to what? It's equal to HA T hot minus T cold, which basically we're going to do the same thing here. This will be Q convection per unit area will be equal to what? H. And again, between what and what? Between the hot surface, which is T surface, minus temperature of the air, which is T naught. Okay. So using these two equations, Q total per unit area, we know it's equal to Q radiation per unit area plus Q convection per unit area So it will be equal to sigma epsilon T surface to the fourth minus T temperature of the surrounding plus H Ts minus T naught. Okay, so if we do the numerical application, what do we have? Let's see here, write down the value for Q. So this should be equal to the 5.6704 10 to the minus 8 units are correct, watt meter square Kelvin. So we'll leave that this way. Times the emissivity is how much? 0.93. Here, be careful. Here we are not doing the difference. This is to the power 4. So you need to use the temperatures in Kelvin, no? You cannot keep the one in Celsius. So that one in Kelvin, the one on the surface is 320 to the fourth minus 300 to the fourth. So this will be for the Q radiation plus, I think was 10. Yeah, 10 watt meter square times 320 minus 300. And this, if we didn't do any mistake, which I'm sure we did not, should give you a value. You see, that's what we get of. Okay, so one is 0.33 kilowatts meter square. Okay, but go and check. Okay, just want to finish on time. So 0.33 kilowatts meter square. All right, so we stop over here for today.